All right. Thanks very much for the great opportunity to share our recent work. And I'm Zhitong Xiong. I am a postdoc researcher in TU Munich and working together with Professor Xiong Zhu. And today I would like to give a talk on our research, recent research on multimodal foundation models for Earth observation. And sorry. I will delve into these aspects to give my talk. First, I will start from the data sets for Earth observation. Then we will look at the SSL4EO-2024 dataset. It's a large-scale pre-training dataset for training EU foundation models. Then I will give a bit more details about our recent work, named the DCAR, bimodal self-supervised learning method for training EU foundation models. And then we will arrive at a research question, why there is a need for unified foundation models. And following that, I will introduce our recent works, including the AlphaNet, a very simple but effective unified EU foundation model, and the DOFA with better flexibility and energy efficiency. And finally, I will touch upon some future research focuses for the development of EU foundation models. And if you can see in this figure, there are more and more data sets with larger and larger volumes published in different years. We can see this clear trend, and this data that are using images from different satellite sensors platforms, including the Sentinel-1, Sentinel-2, and hyperspectral images from the NMAP and the aircrafts. And in the right side, we list some very typical data sets in EU. So you can see that these data sets actually are different from each other in the textures, in the spatial resolutions, and the numbers of spectral bands. This is basically a result of different imaging principles of these different sensors. And then we will look at our SSL4EO-2024 dataset. We built this dataset following our motivations because there was not yet one well-curated multimodal and multi-temporal dataset for training self-supervised learning methods on EU data, and there was not yet systematic benchmarks for self-supervised learning methods for EU data. And so we built this dataset. It is a global coverage dataset covering for different time steps, including for different seasons, and with more than 250,000 locations and more than 3 million patches. And we built this dataset following these different steps. We sample one city and we sample one location and check the overlap, and we check the availability of for different seasons, and we repeat this process. And finally, we download all the images from more than 250,000 locations. And on this dataset, we have benchmarks for different representative self-supervised learning methods, including MOCO, Dino, MAE, and dataset, data for each vector. And we have conducted 5 different downstream tasks, including EuroSet, BigEarthNet, SOTUSet, DFC 2020 for pixel level segmentation tasks, as well as the binary tree detection tasks. And here are some results, some detailed results. We can see that using a large-scale dataset for pre-training the weights and fine-tune it on these different datasets, it works well. So this means that building a large-scale dataset is effective. And we can see from the second table that using contrastive learning-based methods works better than MAE in linear probing setting. And yeah, and from this table, in the left side, we can see when we're using all the multispectral bands for pre-training the model, it works much better than when we only use the RGB images. This makes sense because In the older bands, the information are much richer than the only the optical images. And we can also see that on DFC 2020 and OSCD, these pixel level tasks, the self-supervised learning pre-trained with are also quite useful. We can see the performance is much better than the random initialization. And then I will go into details, a little bit of details about our work. Was just accepted by ECCV 2024. So we can see from the title, DCAR is a model to decompose the common and unique representations from two different modalities. So it is a bimodal self-supervised learning method, actually. So you can see here, if we have a modality A and a modality B, we would like to learn not only the A-B common representations, but also we would like to keep the A unique representations and B unique representations using all these different representations to do a better learning on downstream tasks. Here's a detailed architecture of our DCAR. It actually consists of three different parts. But the first part is the deformable attention part. We're using deformable spatial attention on different data modalities to keep the model learning, focusing on different parts of the modality and to learn the unique features from individual modalities. And the second part is explicitly modeling the common and unique embeddings. We split the feature vector into two parts with a larger portion to learn the modality common features, and we leave a smaller work portion to learn to keep the modality unique features. And this whole network is trained using for different loss terms, including the first one is loss M1 is to contrastive learning loss to learn for the modality 1, and the last one is a contrastive learning loss to learn on modality 2, and in the middle is the interaction between two different modalities. We would like to learn common features and unique features together in our DCAR framework. And here we provide some detailed results. You can see using our methods, we can train on SAR optical, these two modalities, and the performance we can see it works quite better than existing state-of-the-art methods. And during the inference stage, if we only have one single modality, our methods still perform quite well. And a similar conclusion can be drawn on the RGB DEM data. I would not go into details. And more interestingly is for nature images, not EO data, for the RGBD data set, like the Sun RGBD and NYU dataset V2, our method also performs better than baseline. And we can arrive at a conclusion that DCAR as a pre-trained ways can push forward the SOTA performance without any hyperparameter training. And although we have constructed dataset like SSL4EO S12, we have developed the bimodal EO foundation model like DCAR. Sorry. When you then adapt this to a downstream task, like let's say it's only SAR data, will you only use like a subset of the learned representation, the features, or will you always use all of them? So we're like after you train this, and then when you fine tune it for the SAR only task, would you use all the features in the representation or only the ones that were SAR specific? Yeah, we only use the SAR specific features. So everything is learned during the pre-training process. Oh, all right. As we have developed the data set containing two different modalities, and we have developed a framework like a DCAR to learn from two different modalities. But for U data, as we all know, it's far more than only two modalities. So we would like to argue that there is a need for unified EU foundation models. So if you can see from this figure, we can know that the volume of EU data from different data sources is quite big, and it's very suitable to train a very large scale foundation models and quickly adapt it to different downstream tasks. But one problem with foundation models is that it is quite expensive to train. For example, if Google train Gemini Ultra model, it would cost about $200 million. It's quite expensive, and it is also not environmentally friendly. If everyone of us is training foundation models for different data sources separately, and I think the computation cost would be very large. So here we argue that we maybe we only need one foundation model for all of these different modalities, and everyone could contribute to this foundation model and to improve its performance, and we don't need to train from scratch for every different data sources. And this is our motivation of this work. So from this slide, we can see that there are different data sources. They are quite different from each other. So maybe we know that must be some domain shifts between these different data. They're quite different, right? So the research question is a single set of parameters enough to model these diverse EU data? This means that we only use a single set of parameters, a single transformer network that can accept different types of images as input, and the performance is also very good. So to answer this question, actually, we need to know, will the demand shifts between these different modalities affect the performance? Will the foundation model converge? And how to deal with these different input data? And will the performance be better or worse than the modality-specific foundation models? So to answer this question, we have done very simple and straightforward work last year, and this work is called One for All towards unified foundation models for Earth observation. This will appear in this year's IGAS. So I will introduce this briefly here. On the left side, we can see there are some types of foundation models. They are training on different data sources separately, individually. This is quite typical and a straightforward way for to handle different data sources. But could be very computational expensive because you need to develop them individually, and when you are using these pre-trained foundation models on downstream tasks, you need to find the best one. You need to switch between them, and these models can not learn the complementary information from different modalities. And the second type of the foundation model is they try to combine data sources with similar spatial resolution together into a shared transformer. But you can see the third one is our work. We just simply put everything together here. Like no matter it's low resolution, high resolution, or it is Sentinel-1, Sentinel-2, or error images, or it's a hyperspectral image. We just put them everything together using individual patch embedding layers and share a single transformer backbone. So this is very simple, straightforward without any bells and whistles. you can see more clearly here from this slide. Our network, including modality-specific patch embedding layers to transform different data sources into a common feature space, and a shared transformer network to learn multimodal features, common features, and finally we have modality-specific decoding layers to do the reconstruction. So this network is trained using a masked autoencoder. And this is the data set we're using. Actually, it includes 5 different data sensors, including the Sentinel-1, Sentinel-2, Golfin data, and error images from NIP, and the hyperspectral images from Nmap. We can see that the wavelengths, spectral bands, the spatial resolutions are quite different from each other, but we would like to put everything together to train a single transformer network. And here we can see some experiments. We evaluate our pre-trained network on the GeoBench. It consists of 6 classification datasets and 6 segmentation datasets. We are using linear probing for the classification datasets. We can see that AlphaNet works better than random initialization, and the MAE single is a baseline method where we train the model individually for each different data modality. We can see our AlphaNet works better than the baseline MAE single. This means that for these different types of data sources, maybe we don't need to train them individually. We just put everything together, because although there must be some data domain shifts between them, but actually they are observing the same Earth. They must have something in common. So this is our motivation to develop such a model. Now we know that using a single set of parameters in using one transformer actually is enough to model all of these different types of EO data. But this model actually lacks flexibility, and it's not energy efficient because you are trying to combine these different data sources together. It is a very large data volume. When you are trying to train this model, it would be quite computational expensive. So we face these following challenges. The first one is, I think you all know that when we are using EO data, sometimes we just use a combination, a subset of the like Sentinel-1, like the Sentinel-2 data. So the spectral bands could be different. And what happens if new sensors coming up? You have to train a new content model for the new sensor. So, and the third challenge is it's not quite energy efficient. To handle this problem, we developed DOFA, which is inspired by the neoplasticity. Neoplasticity is the brain's ability to change its structure and function in response to new experiences. Actually, when you are learning new things, listening to music, your state of brain is changing. So this is the inspiration. And here is an animation that I would like to describe this process. When there are, as I just said, when you are learning a new language or we are listening to your favorite music, there could be some environmental factors. And these surrounding factors would trigger some chemical signals to your brain, and the brain would cause some change. For example, the axon protein or the synapse remodeling. You can see that the brain is changing its state to enhance the learning ability to new things. So this is the basic idea. And inspired by this idea, we want to model the DOFA with the ability to handle different data modalities. So the first thing is we need to design a mechanism, a dynamic mechanism, so that the model can adjust itself according to the input. So here we design a dynamic weight generator. It's nothing but a hyper network. It accepts the metadata info as input and output the weights of the dynamic projection layers in our DOFA model. And when a new data modality coming in, we accept the metadata info as input, and the dynamic weight generator would generate weights for the new data modality, and we can use these weights to dynamically process the new modality data. And this is the main process. So here the most important part is how do we design the dynamic weights generator? And in this slide, I will introduce more details here. If you are familiar with the vision transformer, you will know that there is a patch embedding layer where you patchify the image into tokens, and then you will transform it using a linear layer. So this is the patch embedding layer. And with our dynamic weight generator here, we accept the wavelengths as the inputs, and it's processed by position embedding module to embed it into feature vectors. And then it goes through several fully connected layers, and it is transformed into wavelength query tokens here. And this, we further add a learnable token pool here into the transformer block. And with the query tokens, we can output the dynamically generated weights here. And similarly, we can do the similar process for the bias token. So using this transformer block, we can dynamically generate weights for different input modalities with different numbers of spectral bands. And the whole network is actually trained using a MAE masked image modeling architecture. And this is the main part of the DOFA. It includes a dynamic projection layer and the shared transformer, as I just introduced in the OFANet. And we also have a shared decoder and a dynamic decoder to reconstruct the image with different numbers of spectral bands. And for example, as the we input the NIP with RGB bands, the wavelength conditioned with generation process will generate the weights to reconstruct the input NIP RGB data. And it's quite similar for the Sentinel-2 data. The wavelength is different, and the dynamic weight generator would generate the corresponding weights for this kind of data, and we will do the reconstruction process here. And so as to the hyperspectral data, and after the model is trained, we can use the model weights, the single set model weights, to fine-tune it on different types of data sources on different downstream tasks. So this is the main process of the DOFA. And another thing we need to consider is about the energy efficiency. As I just said, we are combining so many different data sources into a very big one, very big created data set. It could be very computationally expensive to train such a foundation model for like 100 epochs. So we would like to make use of the resources from the community. Why not use the large-scale prediction weights from the natural domain, from the general domain, like the large-scale weights pre-trained on ImageNet 22K, or the clip model, segment anything model, or the intent image, or a combination of these models. We would like to do the knowledge distillation from these pre-trained weights into our DOFA model, and so as to reduce the computational cost here. But as we all know, RGB images, they are only using three bands RGB, but for the EO data, we're actually using hyperspectral or multispectral data. So there's a gap. How could we do the energy distillation? So thanks to the DOFA can accept flexible numbers of spectral bands. Here we propose to sample a subset of spectral bands from the original hyperspectral data, like we just sample 3 RGB channels, and we import it to DOFA, and we also import this sampled subset of input image to the teacher model. We use DOFA to mimic the teacher model. So we can do the energy distillation using this mechanism. And similarly for the multispectral data. So this is the detailed architecture. We can see that we are using 2 types of loss functions. One is the feature distillation. We use DOFA and the sampled subset of spectral bands as a bridge to do the knowledge distillation from the pre-trained teacher models, and we use the same set of parameters to do the masked image modeling. So in this way, DOFA can be trained using less computational cost. Then it comes to the experimental part. Actually, we're using 3 different experimental settings. The first one is linear probing on the classification tasks. You can see here, we have 2 versions of DOFA, including VIT base and VIT large. On most of these downstream data sets, we can see our model works much better than its counterparts. You can see that for some models, they are not able to adapt to some of these data sets directly, because they are only trained on RGB images, or they are only trained on like Sentinel-2 images. But our model in performance, we're better than them, and in generalizability, we're also better than them. And another experimental setting is we fully fine-tune the model on the BZISC45 dataset. We can see both versions of DOFA also performs quite better than others. And on the segmentation datasets, we're using the setting and we fix the backbone of the network, and we only train the segmentation head. Here we're using the ARPANET as the segmentation head. And very similarly, on the different segmentation datasets, both versions of DOFA works much better than existing state-of-the-art methods. And also on the segmentic dataset, we conduct fully fine-tuning here for 100 epochs, and it also outperforms existing star methods called SpectralGPT. If you know this work, or SpectralGPT Plus, our method is much better. Here we need to note that we are only using a single set of parameters. We don't need to train on different data sources individually, but we can still outperform them using this single set of parameters. So we could conclude that DOFA works better, not only in the performance, but also in generalizability. And here we also realize the dynamically generated weights to see that we can see that for different input images, the spatial patterns are quite different from each other. So this to some extent, this means the generated features, the generated ways are effective. And on the right side, we also visualize the curves of the accuracy. You can see that SOFA actually converges very fast, and the final performance is also better than its counterparts. And at the last, I would like to touch upon some future research focus for the development of EU foundation models. Actually, we are also working on how to benchmark existing foundation models in a fair and feasible way. If you have done some experiments on downstream tasks, you may know that for different pre-trained models, like the contrastive learning pre-trained or MAE pre-trained models, the hyperparameters like the batch size, the learning rate, it influenced a lot on the final fine-tuning performance. So we need to figure out a way to compare these different foundation models more fairly. And another thing is, as we just talked about, when new sensors coming up, when there are new data modalities, do we need to pre-train on these new data modalities from scratch? I think it could be very computational expensive. So we would like also to work on continuous pre-training to make it work with new data modalities. And regarding the data set, I know there is a data set called MMRs. Yes, we also want to build such a data set with geo-paired multimodality and with different sensors. This could be fundamental for developing multimodal foundation models. And we also need to work on the region level and pixel level contrastive multimodal learning, not only on the image level. And for AI assistance, we also need to work on a region level, image level, and pixel level alignment with the language modality to make use of the ability of very large vision language models. And for different tasks and for different EU data sources, we also need to work on the parameter efficient fine-tuning methods on the different downstream tasks. And finally, there should be a real unified foundation model that to unify not only the discriminative foundation models, but also the generative foundation model. For example, if you are training a different model, and if you're you can also use the features from the UNet for the discriminative tasks, not only the generative tasks like generate images. So here I also put our paper link and code to share with you. If you are interested, you can access our papers for more details. And also you can reach out to me to discuss more details. I will be here tonight. And I think that's all for my today's presentation. Thanks all for your attention.